Hello everybody. We are still talking about the unsteady state molecular diffusion in finite bodies, and we have already discussed the four parameters that we have that we use to or use in the charts. So we provide the value of x and m, and then we can get the value of y. And this is what we covered in the last two videos. So now we want to see how the charts look like. So these are the shapes of the charts. We have here three charts: one for the slab, one for the cylinder, and one for the sphere. Now, you see here at the top right corner of each one of them, it gives you a photo or kind of schematic of the shape that we have. It gives you here the slab, and it shows you not only that this is for the slab, it tells you where is x and where is x1. The same for the cylinder and the same for the sphere. So in case you forgot what is the shape of or the meaning of x1, this is going to be a quick reminder for you to refresh your information. For the three charts, you have the x-axis is x and the y-axis is y. This is here and this is here. So and you see y is from 0.001 to 1, and then we said that the limits of y is from 0 to 1. So this is gonna be the minimum value on the chart, and this is 1 the maximum value on the chart, and the same here and the same here. And this is the output that we get from the chart. So we need to find the point here, and from this point we can go and find the value of y that represents this point. For the x-axis is the x. Its limit is from 0 to 6 for the slab, and from 0 to 3.5, and 3.5 in the cylinder and the sphere. Then we have two of the four parameters are already there on the two axes, and then all these lines should represent m and n. So for each one of them, you would see there is a group of lines that are a group of parallel lines, and it's a different group. So we have different groups of parallel lines, the same here and the same here. And for each group, you would see that there is m equals 0 here on the right and to the left of this group, and the same for the next. It's m equals 0.5, m equals 1, m equals 2, and m equals 6. The same here, m equals 0, 0.5, 1, 2, 6, 0.5, 0, and so on. So for each group has a constant value of m, and each line in this group represents a constant n. So here it is, the leftmost line here is n equals 0.8, then 0.6, 0.4, 0.2. So this is what these arrows represent, and the same for this group and this group. So given my inputs that I have the value of m and the value of n and x, so if I have I know the value of m and n, then I know which line I am going to use. So first, before everything, I have to pick the right chart for my system. So based on choosing the right chart, I'm gonna go for the rest of the input. So let's say I have the cylinder, so I have m and n with whatever numbers. Let's say m equals 1, so this is the group of lines that represent m equals 1, and then I want n equals, let's say, 1, so this is the line that represent n equals 1. So I need one more information to pick one specific point, and this information is the value of x. So if x equals 2, then I will have y here somewhere. Here it's almost 0.035 or something. This is how we use the chart. So it's pretty simple and it's pretty straightforward. The maybe the only part that is important or tricky in it is to get the right values of x, n, and m, and this is it. So now let's try an example here for a drug capsule. So for this drug capsule, it's a sphere. It consists of 0.652 centimeter diameter spherical bead. It's loaded with uniform initial concentration of 68.9. This is Ca node of dramamine. It's just a drug, which is the active ingredient, species A, that's diffusing, and it diffuses through the bead to the body. So when you take this drug capsule, the active ingredient starts to diffuse from inside the capsule to outside, and then it's swept by the body fluid. And it says here it's quickly swept by the body fluid, which means that the concentration of the drug outside the this spherical bead is 0. And then the convection mass transfer resistance is negligible, so there is no resistance to mass transfer by convection outside. I know the diffusion coefficient of Dramamine in the gel matrix or in the material from which the capsule is made. It's 3 multiplied by 10 to minus 7 centimeters square per second at body temperature. So this is the operating temperature, which is constant. Of course, it's an unsteady state molecular diffusion process because there is no constant source. It's just the amount that I have inside, and as time goes, it's getting consumed. So it's not a steady state case. I want to know what is the residual concentration of Dramamine in the center of the spherical bead, at the center, at R equals 0 after 48 hours. So this is what I want to do. So I have here the chart for the sphere, and I will put the inputs that I have. So I know the concentration, the initial concentration. See, I know the 68.9. I know the initial the concentration at the surface. It's gonna be 0 milligram per centimeter cube. I know that the x1 is, as it says here, x1 is the radius, so it's gonna be 0.326. And I know the diffusion coefficient, and I know the time is 48 hours. I have to multiply it by 60 by 60 to make it in seconds, so it has the same units as the units of time in the diffusion coefficient. So from these three, I can calculate the dimensionless time, which is xd, or x. It's gonna be 0.488, and I know that the diffusion coefficient is much bigger than the mass transfer coefficient is much bigger than the diffusion coefficient. So this will make m equals 0, but now I know n equals 0 because x equals 0 because it's at the center, so radius equals 0. I know m equals 0, and these are the three information that I want to know so that I can get something out of the chart. So let's see if I have the xd equals 0.488. Let's go first for the line that represents m equals 0 and n equals 0. So for m equals 0, this is the group. N equals 0 is the rightmost line on this in this group of lines. So it's gonna be this line. This is the line that represents m equals 0 and n equals 0. And given that xd is 0.488, which is gonna be almost this value, then you can get the intersection between these two lines, which is this point. And if you go to the left, you will find the value of y, which is gonna be between 0.01 and 0.02, which is gonna be 0.018. This is gonna be kind of little. It's not very accurate. It's a little approximate value because somebody might have the same chart and get a different value. It's going to be close, but it's not might not be the exact value. So this is going to be 0.018, which is equal to CAS minus CA divided by CAS minus CA node. So from this I can calculate the value of CA at R equals 0 and at T equals 48 hours, which is 1.24 milligram per centimeter cube. So this is a simple and straightforward process that we can follow to calculate the concentration from the inputs, and this is what we are gonna cover for this part. The next video we are gonna it's gonna be the last video about this topic, which is the molecular diffusion, or using the charts for molecular diffusion in 2 and 3 dimensional diffusion, and this is gonna be the topic of next time. So I'll see you then. Goodbye.